Hello everyone. Uh, so today we'll study chapter 2 part 2. We'll first study the observed likelihood in section 2. So that is the which is the likelihood on the missing data. So we'll first introduce the concept of the observed likelihood. So here's the setup. So we have an independent realization of random variable y with the density f, y set a null, and we have a indicator function for the missingness. So basically this random variable. So this is another random variable, and this random variable follows this mechanism, right? And so under this 1 and 2, instead of observing y and delta, we observe y and y observed. I mean delta and y observed, and where the y observed is either, so if delta equal to 1 is y, delta equal to 0 then is nothing, no information. So the question is, what is the marginal density of the y observed and delta? So here's to answer this question, we use the following change of variable type technique, or using the that basically came from the induced probability concept. So suppose y is the z is the original random variable with the known density function, and instead of observing z directly, we observe y, where the mapping z to y is known. Okay, and then turns out that the density is this one, where the ry is the set of z that yz is equal to the given. So this is a given, right? So this is fixed. Then for that given y, we find z such that yz is equal to y. Okay. How do you derive this? Okay. So see, so this one is y. You can write it. Okay. Because all you know is this one, right? So because you know this one, so this is actually the random event. Oops, too large. The random event that y random variable y belongs to z is the equal to yz. It belongs to b, right? So that is this one, and so that you can write it as a z random variable z belongs to y inverse b, which is this one. Okay, so then this is using this concept, you can actually consider a CDF, right? So this is the CDF of y, and that is actually, you can think it as a z where y z is less than t, that f z dz. Okay, so that is the CDF, and but we are interested in obtaining PDF. So we want to compute. So GT, okay, the PDF we use G. So GT is dt of CDF. So that's basically dt of this guy, right? So see, this is so you can see that this part is, oops, sorry, dz. So you can okay, dz, and so you can see that you are interested in the computing the uh, differentiation with respect to t. So that's only this part. So that's basically the boundary, right? Boundary of the set. So that's this one. Okay. So that gives a justification of the density concept. Okay, I'm gonna use the toy example to illustrate the idea. Okay, so z is a random variable with support with equal probability. That's very simple example. And the mapping is this. So if z is either 1 or 2, then y equal to 1. If z is 2, 3, 4, 5, then z is equal to y is equal to 2. Okay. And then question is, what is the marginal distribution of y? That's easy, right? So because we know, so the random variable y is just either takes the value of 1 or 2 with the probability p y equal to 1, which is p z equal to 1 or g equal to 2. So that is the 2 over 5 with the probability equal to z equal to 1, 2, oops, 3, 4, 5. So that is the 3 over 5. So that is the answer. Okay. So that provide the answer to the example. So then now the main question is this. Actually, the original question is, what is the marginal density of the y observed and delta? Okay. So the z. So if we are going to use this idea and apply it to our problem, so then z corresponds to the original data, which is y and delta. So that has a density function. Okay. So f1 is the density of y, marginal density of y, and then f2 is the conditional density of delta, conditional on y. Okay. And then second step. So step 1 is the specifying the original density. Step 2 is the specifying the mapping, right? So the step 2 here is the mapping. Mapping is this. Okay. Right? So y observed is just y observed is, actually we can, to be more accurate, this is the mapping is y delta to y observed delta. Okay, so this is better. Okay, so then marginal density of this guy is using is this one, right? So we have only to determine the set ry observed delta, y observed, and delta. So what is this? Well, you can see that if delta equal to 1, then this is just y, right? And if delta equal to 0, then this is just the support of y. Okay, so that basically, so this is sy. So that gives this answer. So if delta equal to 1, the set is here, the set is y. So you just compute it, evaluate it at y and delta, right? And delta equal to 0, then we have to integrate over over the whole support. So that gives this answer. Okay. So that provides us to present the likelihood on the missing data, which is the observed likelihood. So the observed likelihood is the likelihood observed from the marginal density. Okay. So that using this, so we already computed the marginal density already. So if delta equal to 1, then this is the original density. Delta equal to 0, we have to integrate out over the missing part. That's exactly what we are doing. So at delta equal to 1, we use the original density. Delta equal to 0, we need to integrate out over y. So that's what we do here. And then see and then what is f2? We spell out f2. The f2 is this one. So spell out f2, then we can write it this way, right? So then turns out that this one is not independent. I mean, it's a free of zeta. So we can treat it as constant. So c can go outside, and this is the part that depends on function of zeta, because we care about zeta only, right? Okay, so that's the known pi y is known case. And now question is, what if pi is unknown, has an unknown parameter, so something like this. Then we don't have, so derivation does not work here if in this case, because it's no longer constant. It's actually unknown parameter. So the parameter is now becomes zeta and phi, and then we have this factorization. Okay. So that's the observed likelihood. And example, so example 2.2 is a popular model, Tobin model, and it's a very popular classical example in econometrics. So please work out for yourself and see whether you get the same answer here. We'll cover it during the live class. Okay. Example 2.3 is a censoring data example. So so you can please work out for yourself and see whether you get the same answer. So this is actually you observe y, so it should be y here, yi here. That's the answer. But other than that, the answer should be correct. So you can try for yourself, and so we'll discuss in the live course. Okay.